Hello students of statics, this is Dr. Dan Baker, and today's video is going to focus more on trusses, and we're going to continue this idea of what is a simple truss. In the simplest definition, you can think of simple either meaning made of triangles. That's kind of the visual clue if you have a simple truss. Another way of talking about simple is fundamentally solvable in statics. If you have other kinds of trusses which do not classify as simple, then we're going to need some more equations which we don't have yet in our problem-solving toolkit. So this idea actually builds upon stability and determinacy, which we talked about for single rigid bodies. Okay, so for a truss to be classified as, quote, simple or solvable in statics, we need three things to be true, okay? Actually, let's go with four things, just because we listed it out as three things coming out of our rigid body chapter, so we'll add one more to make four, okay? So let's go with number one. It needs to be externally stable for translation. So just like rigid bodies, essentially we don't want parallel supports, okay? Number two, it needs to be externally stable for rotation. And this is based upon the intersection of the lines of action. Remember, we don't want one single point of intersection for those lines of action of the support components. Number three, it needs to be externally determinate. And of course, externally determinate looks at the number of equations versus unknowns. Okay, so we talked about we wanted n is equal to 3. So let me add a couple other notes here. 2 points of LOA intersection. And the top one here is not parallel. Okay, so those are exactly the same. As for a single rigid body. If you don't remember those, you can go back and look at the stability and determinacy videos related to single rigid bodies. So the new rule that we have, because now we have a truss, has to do with internal determinacy, okay? And so you can think of that two different ways. One is you can think of that we have internal determinacy, which you could also think about being internal actually make a little modifier here. This is no internal redundancy. Now, redundancy in engineering design is not necessarily a bad thing. Okay, if one structural member breaks, that another structural member could step in and do the work of both of them. That's not a bad design plan. But here in statics, we actually don't have enough equations to handle redundancy on the inside of trusses. Okay, so we're going to be stuck building these or analyzing these simple truss systems, which to be honest, some people call fracture critical trusses, because if one single member breaks, the whole rest of the truss is actually going to collapse. So we know that all topics of determinacy here in statics are based upon a balance of equations and unknowns. Okay, so we know that our unknowns must equal the number of our equations. Technically, we could have fewer unknowns than equations, but we'll just go with equality. And so the unknowns in a truss come from two things. One is they come from members, right? The tension or compression inside each member, each rigid two-force member. And then we also have our supports, or I listed here as our reactions, right? Because reactions are the forces and moments which come from supports. And here we're going to stick to similar to or the same as a rigid body. We're going to go with 3. And this must equal the number of equations. And so if you think about the number of equations in a truss system, it's going to be based upon your force equations, and all of your force equations come from the number of joints, right? So we have 2 equations per joint. So fitting variables to this, if we call the members M, the joints J, and the reactions N, we could say that we need M plus 3 is equal to 2 times J. So this is your essentially 4th validation to having a truss which is solvable in statics. And so there may be some problems that have you go through and there'll be a series of trusses and you have to basically go through these 4 different options, these 4 different tests to make sure that it is externally stable, that it is externally determinate, and also internally determinate. Now I've ordered these in this way because this is actually the quickest way to go through them. Now I suppose you could put this externally determinate even above here, that's kind of your choice. But certainly doing external first, this internal analysis does take the most amount of time. So if you end up, just as this is kind of context off to the side, but if you end up with M plus 3 greater than 2J, what do you think that means? What do you think that means physically? You have an extra member, right, fundamentally, if we're still sticking with 3 reactions. So this is actually a case where we'd have redundant members. Probably your safest design choice, but a design choice that we can't analyze here in statics. If you end up with M plus 3 is less than 2 times J, this is a very bad design choice. If we only had enough members in a simple truss to keep it rigid, if we take one of those away, this is going to be internally unstable. And fundamentally, you're going to see squares instead of triangles. Okay, so if you see a square opening in a truss, now there could be some situations that you could work really hard to create a square and it might be okay, but in general, a square in a truss is bad because that square can actually flex and bend where a triangle can't. Let's take a look at the implications of having a simple truss, which I mentioned also can be called a fracture critical truss. Now you may think that, well, statics have been around for a long time, we've been designing bridges for a long time, that we've probably gotten rid of all of these simple trusses, which are bridges. Turns out we haven't. This is a little bit older of a failure. This was back in 1967. This is on the Ohio River, And essentially there's two different bridges right next to each other. One of them had a simple truss design. That bridge was completely loaded with cars, 5 p.m. rush hour. It's December 15th. That river is cold. 31 cars fell into the river and about 50 people died. So you can take a look at this link from nist.gov about the Silver Bridge for more engineering details. So you might think, wow, that was like 50 plus years ago, no big deal. Here's a failure from 2013. So at the recording of this video, this was 7 years ago. So this is the I-5 bridge over the Skagit River. So I-5 runs up the west coast of the U.S. Now this was in May, so probably quite a bit of water in the river with spring runoff, but at least not as cold as air temperature. 7 p.m. And there was a cross member, and this was a cross member coming across the top of the bridge, and the bridge had a really low overhead height. And so it was posted, but multiple trucks had either misjudged or mismeasured their truck height and had hit this span of the bridge. Now, bridge inspectors had taken a look at it and say, it's okay, it's okay, it's okay, and then it wasn't okay. That one member failed. The entire truss collapsed on itself. Now, luckily, there actually were some pleasure boats that were in the river near the bridge, and so no one was actually killed. Any of the cars that fell into the river actually were picked up by the boats, and so no fatalities in this one. But there are still a good number of these bridges out there, and this is one of the things contributing to kind of our poor bridge rating in the US, that we need a lot of our bridges replaced. But bridges are very, very expensive to replace, and so it'll be a long-term process. So that wraps up this lecture video on trusses. Hopefully this gives you a little bit more context about what exactly is a simple truss, and then also if you choose to design a simple truss, what some of the engineering implications might be. Hope you're having a great day.